Hello, we are Canary and Coalmine Designs. Our team consists of Jeffrey Weiss, Avish Menon, Nathaniel Soderberg, and me, Zachary Riley. We have designed a handheld device to send a sensing signal to a remote radiation detector, allowing measurement from a distance of potentially radioactive sources. A potential application of this product would be in the protection from nuclear threats and radiation safety, as a container or other object could be lined in the sensing array, and a single handheld interrogator could then be used to check the radiation levels detected by each discrete sensor. Next, we're going to be showing an animation to walk you through how this device is used. So this transmitter works like this. First, a sawtooth wave is sent into a VCO that sends out a signal. From this signal, we're going to be sending it through a circularly polarized antenna so that it will bounce off the array and come back to the receiver. Now, we will also be having a receive antenna that is separate from the transmit antenna. Both of these will be circularly polarized, but in opposite directions. To further enhance the separation between the transmission and the receiver, a barrier of an RF blocking material will be placed between the two antennas. When the signal is sent from the transmitter, it will bounce off the sensing array, reverse its polarization, and be able to be picked up only by the receive antenna on the other side, effectively blocking out most noise.
So here we have some hardware that I've built for our project. This is the proto board of the ramp signal that will feed into the voltage controlled oscillator to produce the chirp signal. So what happens is VDD is here. I'm putting in 6 volts VDD. And here's ground. This is pin 2 where the output is. And so what happens is that it outputs a ramp signal with a period of 120 microseconds, voltage peak to peak 4.25 volts, Vmin of approximately negative 6.25 volts, and Vmax of negative 2 volts. So as can be seen here, that's the output ramp signal, and here's the schematic.
So when the signal, after being reflected off the target, is picked up and processed a little bit, it should have a spike in its intensity that corresponds to a certain frequency of the chirp signal that originally hit the target. This Verilog code is meant to detect the timing of the spike and would be implemented to an FPGA. It works by first syncing the clock with some fraction of the period of the chirp signal. Then a counter is set up that resets on each period. The counter is then used to find out how many clock cycles it takes from the start of the signal to where the spike occurs. And then multiple readings are averaged out just to get a better result. This is where the code ends currently, and with our data, the simulation is giving an average of about 29 clock cycles. So for our clock period of 3.9 nanoseconds, this would be a delay of about 113 nanoseconds. And for our chirp signal specifications, that means the target is reflecting frequencies most strongly about 5.75 gigahertz according to the Verilog output, which is very close to the 5.8 gigahertz peak. That is what the target is supposed to have.
And that wraps up our demo. We are Canary and Coalmine Designs, and thank you for watching.